So in this lecture, I'd like to introduce the concept of angular momentum, and this accompanies Matter and Interactions, your textbook by Shafee and Sherwood, Chapter 11, the beginning section 1, and your supplementary textbook, Klippner and Kolenkow, An Introduction to Mechanics, Chapter 7, sections 1 and 2. So, first of all, we're going to introduce a new idea. And that idea is that a particle can have an angular momentum. And so this is the rotational analog to the regular momentum p, which is, of course, classically defined as the mass times the velocity of the vector. So you can find the angular momentum of a moving object about any point in space. So what we generally do is draw a coordinate system and then find the angular momentum of that object with respect to the origin of the coordinate system here. But be aware that you can find the angular momentum with respect to any point, and indeed in an example later we'll find the angular momentum with respect to two different points and show that it's not the same, okay? So here though, to get us started, the angular momentum, which is often symbolized with the capital L, right, and it's a vector, is equal to the cross product of the position vector with the momentum vector. Now the angular momentum can change in time, and so we're talking about the instantaneous angular momentum with the instantaneous position and the instantaneous momentum vectors. So you can see here that we've got the vector r, the position vector r, pointing from the origin to the point in question. And then that object is moving with a momentum p, right? And then you have the angular momentum here, indicated by the green arrow, is the vector cross product of r and p. Now that makes the SI units of the angular momentum, the units of r, of course, meters, and the units of p are kilograms times meters per second. And so the SI units of angular momentum are then kilograms times meters squared divided by seconds. And we don't have a special name for this unit, we just leave it kilograms times meters squared divided by seconds. Alright, now both the magnitude and the direction of the angular momentum depend on the choice of origin or the point about which you're trying to find your angular momentum. So if you change the point, you change the value of the angular momentum because the position vector r will change. Alright? Now since it's a vector cross product, the magnitude of the angular momentum L is the magnitude of the position vector times the magnitude of the momentum vector times the sine of the angle in between the position and the momentum vectors. Writing that out, you get the magnitude of L is mvr sine of theta, where theta is that angle. And of course the direction of L is going to be perpendicular to the plane formed by the position and the momentum vectors. And you can find the direction, of course, via the right-hand rule. Now, a lot of people, when they think of angular momentum, think of the following picture. You have uniform circular motion, right? So maybe you have a satellite orbiting planet Earth in a circular orbit, for example. And the speed of that satellite doesn't change with time, so it's a constant speed. And so what happens is you have a position vector that is then pointing from the origin, which would be maybe the center of the planet, to the satellite. So that's a radial vector, right? And then the momentum of that object is going to be perpendicular to the position vector always if it's in a circular orbit. And that's because, of course, the radius and the tangential components there, the radius and the tangent to the circle, are always going to be perpendicular. And so that means that the sine of the angle in between your position and your momentum vector is 90 degrees, and the sine of 90 degrees is 1. And so then you can write your angular momentum as L is equal to mvr sine of 90 degrees, which is just mvr, okay? So this is a pretty typical way to think, but just bear in mind that it doesn't always have to be this way, okay? It is for circular orbits where objects are in constant circular motion, right? Uniform circular motion, but it doesn't have to be that way always, okay? Your angular momentum can vary in time, and your position and momentum vectors do not have to be perpendicular to one another for different types of problems. Now, just like so many other vectors, angular momentum obeys superposition. And so what that means is that the total angular momentum of a system of particles is going to be the vector sum of the angular momenta of the individual particles. And if you're talking about a specific object and you have angular momentum from different components, as we'll discuss later, then that obeys superposition as well. In other words, you add them up. Remember that this is a vector sum now, okay? Because it's a vector sum, you can't just add the magnitudes up and call it a day, okay? They have components to them, and you have to add them via vector addition, as is shown in this equation here, where L total, the vector L total, is equal to the vector sum L1 plus L2, and so on and so forth. Now, if we break our position vector into components that are parallel and perpendicular to the momentum vector, as is shown here in this picture that I borrowed from your textbook, Kleppner and Kolenkow, right? So here we have a position vector R and a momentum vector, right? And R and P are not perpendicular to one another. But we can break R into components that are parallel and perpendicular. And the R perpendicular, the R perp, is shown here, right? And so what we can see there is that if you work out the angles, here the angle in between R and P is this angle phi given here, okay? And then if you look at this, you have this vector R, which makes the hypotenuse of this right triangle, and your R perpendicular is the lighter line that's shown. So here R is the hypotenuse and R perp is one of the legs. Okay, and then it intersects with P here, and it makes a little 90-degree angle. So this is a right triangle. So the angle on the interior of this little right triangle would be pi minus the angle phi, right? So that's the angle there. And then if you think about it, the magnitude of R times the magnitude of P times sine of that angle phi, right? So R sine of phi would give us this R perp, right? Because it forms this right triangle, and the sine of this pi minus phi angle, sine of pi minus phi, would give us R perp divided by the hypotenuse magnitude of R, all right? Now, by definition, the sine of pi minus an angle equals the sine of the angle, and so that means that R perp over R equals sine of phi, okay? Which means that R perp is R sine phi. So we can write the magnitude of our angular momentum L as R perp times P. Or you could look at it that way, R times P perp, because it would be the same thing. And that's shown down here in this picture, okay, where you have R and P, and you break P into components parallel and perpendicular to your position vector. So you could think of it either way. Generally, though, honestly, people talk about breaking R into components a lot more often than they talk about breaking P into components. And so people will say that the angular momentum is equal to the component of R, the position vector that's perpendicular to the momentum vector. So if you take the magnitude of that R perp and multiply it times the magnitude of the momentum, then that will give you your angular momentum. Now, if you think about it, this makes perfect sense. Because of the sine of theta, right, any components that are parallel to one another from the position and the momentum don't contribute, right? So it's only those perpendicular components that will give you a magnitude of an angular momentum. All right, let's do an example problem. So this one is from Kleppner and Kolenkow, and I borrowed one of their images there. So you have a tiny block of mass m, and it's sliding freely along the x-axis. So it's traveling, say, to the right in the plus x direction, and its velocity can be written as some speed v times I hat. So what is the angular momentum of this block, a tiny little block, about the points A and B in the figure? Now, A is the origin. Okay, so A is the origin of this coordinate system, and B is on the y-axis offset from the origin by a distance L. So it's a distance L above the x-axis. Okay, so those are the 2 points as shown in the figure A and B there. Okay, so let's work this out. So first of all, for the angular momentum about the point A, then the position vector would point from the origin to the point in question, which points directly along that x-axis. And so your RA vector would be equal to some magnitude times I hat, right? Now, we already have a momentum vector, m times v, where it's mv I hat. All right. Now, the angle in between those two vectors is 0 because they both point along the x-axis. And so that means that the magnitude of the angular momentum would also be 0 because, remember, the sine of theta component from there, and the sine of theta is the sine of 0, which is 0. So the angular momentum about the point A is 0. But it's not going to be 0 for point B. Okay, and this illustrates the idea that the angular momentum about different origins or points of the same object will not necessarily be the same. Okay, so here, if you were talking about the position vector RB, it would point from the point here on the x-axis or on the y-axis where y is equal to L and x is equal to 0, and it would point from there down to the x-axis where the mass is. Okay, so it points down and to the right. Okay, so if we write the cross product there, LB would be RB cross P. Okay. And remember that to find the angular momentum from this cross product, what we're going to have to do is take the determinant of this little 3 by 3 matrix, okay? And if you don't remember that, make sure you go back and watch the cross product video to refresh your memory on how to do this. So what we do is we put in the top row our unit vectors, I hat, j hat, and k hat. In the second row, we put the components of the first vector, which here is the position vector RB, okay? Now, it doesn't really tell us where on the x-axis this is, so I just called this distance from the origin to the point in question R parallel, okay? And then the y component there of my vector RB would be minus L because it points from point B, which is in the positive x-axis, down towards y is equal to 0. So that gives you minus L for the y component. And then z is 0 because everything takes place in the xy plane. Now the momentum vector is a little simpler. The momentum vector just has an x component, so the velocity is in the plus x direction. So I write here momentum is mv plus mv in the I hat direction and 0 for the j hat and the k hat directions as such. All right, now we take our little determinant of our 3 by 3 matrix. Remember what we do is we start with the top left component, we cross out that first row and that first column, and then take the determinant of the resulting 2 by 2 matrix. So that would be I hat times minus L times 0 minus 0 times 0. So our I hat component is 0. And then we move on to the j hat component. It's minus j hat times, and then cross out the second column in the top row, leaving you with the 2 by 2 determinant R perp times 0 minus 0 times mv. And so that gives a 0 j hat component for this bit. And then move on to the k hat component. It's plus k hat, crossing out third column in top row, 2 by 2 matrix that results R perp times, R parallel times 0 minus L times mv. Okay, and this is the only part that doesn't give us a 0 value here. So what we end up with is k hat times mvl. Okay, so mvl k hat, and that's our resulting angular momentum. So I think what this does is illustrate that the angular momentum of the same object with the same momentum, but with respect to different points, will give you different answers for your angular momentum because of the position vector change. All right? Okay, I hope that made sense, and I'll see you around. I'll see you in class.